in this section, section 7.2, we are talking about confidence interval. Okay, so this is the lower bound and this is the upper bound, right, of this confidence interval. Why this 1.96, whether positive or negative? Because of this 95%. Okay, yeah. Okay, so I told you last time width is not random, only the center is. Why width? Because this width, it doesn't matter with whether x bar is changed or not, it keeps it width. Okay, so this is how we interpret. I told you this is the way how we interpret, but we use different interpretation to interpret this confidence interval. Okay, okay, let's see how we use confidence interval for mu. So still we are using 95% confidence interval. Okay, so if we have different observations, xn to xn, x bar, okay, same as last slide, we can use like this. Okay, and you know why we use x bar? Because x bar is the point estimator for mu, right? So that's why we use x bar. So you can, these intervals, you can confidence intervals, you can write like within brackets like this, using upper bound, lower bound and upper bound, or you can simply use using greater than, less than symbols. Okay, okay. If you consider a few samples, okay, let's say in this class I'm taking 5 students, so I can pick 5 students, like I can pick 10 12 groups. Okay, 10 12 different groups, and when I calculate their mean, sample means, okay, if I consider 10 groups, I have 10 sample means, right? So like this, this is my population, which means all students in my class, and this is the population mean. Okay, that's the actual mean. Once I pick first sample, I can see, okay, mean is here. Once I pick the second sample and calculate the mean, I can see its mean somewhere here, right? Okay, let's say height of students. So something like that. If I pick different samples, they are mean. Okay, these are samples. These are different samples. Different samples. Okay, so red color dot mean, it's mean. Okay, so you can see they have different mean. In this confidence interval, what we are going to do is we try to catch as much as possible means within our confidence interval. Okay, so for an example, if I pick this interval, okay, this is an example. If I pick this interval, you can see how many means in my samples I can pick. I can uh, I can consider within this interval, right? See, these ones, this one and this one, they are outside of my interval. Clear? So we always try to uh, cover as much as possible. Okay, if we consider 100 samples or 1000 samples, it doesn't matter, we should be able to cover those sample means in our within our confidence interval. Okay, clear? So this mean, this sample mean covers within this confidence interval. Okay, clear? This sample mean, okay, yes, it also covers within this confidence interval. But here, this one, these ones, they don't, right? So you can see we can increase our uh, interval, right? Once I increase like this much, see, they cover almost all sample means, right? Clear? That's how we do in this confidence interval process? We try to catch as much as possible. Okay, we can increase. You can see we can increase from here to here, right? But we don't do something like that. Okay, so this is the sorry, this is the idea behind confidence interval. Okay, okay. Check this example. We have 100 samples, and they have given sigma and sample mean x bar. So once we have these three values and confidence interval, what is the confidence interval here? 95%. So we can calculate the interval, confidence interval. Okay, so you know this is the equation we got from last slides. Okay, plug the values and you can get these values. So 95% confidence interval, mean soda volume is between these two values. Okay, 12.05. Once you simplify this, you can get these two values. This is the upper bound, this is the lower bound. Okay, you can write it like this, or at the end you can write what you got like this: 95 confidence interval, or you can use CI, that's fine. For mean soda volume, because we are using mean soda, sorry, we are using here soda cans. Okay, is so mean of this soda can volume is between these two values. Okay, we don't know what's the exact value, but definitely within these two values. Okay, okay. See, this is the I mean pictorial way to define it in this interval. Okay, okay. Up to this point, we have discussed, or you saw how we calculate the confidence interval for 95% confidence interval. Okay, 95%. Here, right now, we are dealing with not 95%, we are dealing with any percent confidence interval, any percent. Okay, that one we define like, we denote like 100, 1 minus alpha percent. This is how we denote it. Okay, any percent confidence interval. 100, 1 minus alpha percent. Okay, so if you have something like this, I mean confidence interval same as 95%, but here we don't have 95%, so that same equation, but z-score value, it depends on your alpha value. I'll tell you what is alpha. Depends on this. Okay, right now it's not 1.96 as we used last time. Okay, here see, it is 1.96, this one. It's because we use 95, but here we use different one. Okay, only difference is that one. Clear? So this C alpha, standard normal curve, critical value. Okay, so population deviation, standard deviation, any sample size. Okay, let's see what is this alpha. Alpha we call significant level. Okay, we call significant level. It measures the area under the curve to the right, always to the right. Okay, it is something like this. This is your normal curve. I didn't do this part in your normal distribution section. Okay, so if I pick sorry, area something like this, let's say for an example 0.05, this area equals to alpha. Always alpha measure to the right. Okay, some point to right. Okay, that's the definition of the alpha or significant level. Okay, so always to the right. Okay, if I tell you what is the z-score of alpha, z-score for alpha equals 5%. You know this is 5% mean 0.05, right? So what is the z-score? Simply go to the table, okay, find the area of locate the probability or area. Okay, they are same here. Find this probability and pick the C-score values. Okay, clear? So that you can get value C-score C alpha here, this value. This C alpha means C-score value. Okay, alpha mentioned here is in this case it is Z 0.05. This is how we denote C-score for alpha. Okay, clear? I think I didn't mention in our normal distribution section, since standard normal distribution is symmetric about 0, okay, about 0, if you pick, let's say 5%, which means 0.05 from right hand side, then that area, if you pick same area from your left hand side, let's say 0.05 from here, this C value, C-score value, same as this C-score value but different sign, right? If this is positive, then this guy is negative. If this is positive 1.96, this is negative 1.96. Okay, so once you need to find the Z alpha, you can use this area or this area and flip the sign.
Okay.
It is like it's because of the negation, like P dash equal 1 minus P. Do you remember that? That's the idea behind it. Okay.
Okay. Thank you, sir.
Okay. So once they have mentioned C alpha, alpha is 0.05. If alpha is 0.05, or they will give something like this, 5%. Significant level is 5%, something like that. So C alpha means Z 0.05. You have to go to the table and find this area and then find the corresponding Z value. Okay, that's the C alpha mean. Clear? So to find that, you can use like this. You can use these two ways. As I mentioned here, you can simply go to the 0.055 area. It is in the table 1. So you can find the corresponding C value. Definitely it is a negative value. Okay, it's a negative value. Clear? Or you can get the negation, 1 minus alpha. 1 minus alpha mean everything from here to this point. You can find this value. It is a positive value. Okay, both are same. I mean, values are same but different signs, negative, positive. Okay. You will need that idea. I simply copy and paste your standard normal table here because I need to see few things. So these are 3 different confidence interval we are using. Okay, 90%, 95%, 99%. So corresponding C alpha value. Okay, sorry. Okay, here, why this is C alpha over 2? Because we are considering 2 standard value. I mean, since we are considering interval. Okay, so since we are considering interval like this, that's why we use alpha over 2. We call this two-sided, not alpha. They have, okay, in the question you will be given like alpha. Okay, clear? So if you give alpha like 0.05 or 5%, what you have to do is you have to get alpha over 2, which means 0.025. Okay, right now I'm talking how to find the confidence interval using C alpha. Okay, so here you have to see alpha over 2. Don't forget it. Okay, let's go to that slide. That's why they have mentioned C alpha over 2. So here alpha value is what? Confidence interval 90%. 90% mean everything up to somewhere here. So this covers 0.9. This covers this area to the right. It is your alpha. It is equals to 10% or 0.1. Clear? That's how we define it. Confidence interval, so just the idea, okay? Just the idea, okay? This is what this means. But since we are dealing with confidence interval, this gonna be like this. So we pick the area 90% or 0.9 like this. Okay. This area is alpha over 2. This area is alpha over 2. Okay. We get the middle area. So two tails, left hand tail and right hand tail. Those are alpha over 2. Those are equal alpha over 2. So this piece equals to, according to this one, 0.05, 0.05, and this is 0.05. Clear? Same here and same here. Okay, so you can see from left to right, alpha value is decreasing. Okay, so once you go to the table, in this case, you have to find what? This is the C alpha over 2 value. You can go to table and find it. For an example, I'll show you this one. Okay, you need to find 0.05. So I'll use table 1. You can use table 2 using 1 minus that value. I'll use table 1, 0.05. 0.05. 0.05. Somewhere here. 4, 5. See? 0.05. It's not 0.05. Okay, so you have to get the middle value of these two because they have same difference with the 0.05. So negative 1645. See, that's the C value. Okay, negative, but here they just consider positive because once you use the table number 2, second table, you will get the same value but positive. Okay, clear? So it is better you can remember these values so that you don't need to find those values from the table. Clear? Okay. Okay. For this example, simply you can plug your Z alpha over 2 to this equation and find the confidence interval. It is easy. Same example, but here confidence interval is different, 99%. So corresponding Z alpha, alpha over C alpha over 2, not C alpha over 2 is this one. See, these values you can find from the table. Okay, but if you remember these values, you can simply use it. So once you plug that value, this value, then simplify, you will get I think this one, right? No, not this one, right? For the one above is it belongs to this one. See, 12.129 is this one. This belongs to this belongs to 95% confidence interval. This belongs to right here. This one belongs to 99% confidence interval. Okay, here I have used this because I need to compare these two values. Okay, what you can see here with these two values, two different intervals, there are two different intervals for 95 and 99. What you can see, so 95% confidence interval is something like this. Okay, but you can see 99% confidence interval something like this. Check the values, check the gap between those lower bound and upper bound. Clear? So the idea here is once you increase the confidence interval, okay, once you increase the confidence interval 90, 95, 99, with, I mean, gap between the lower bound and upper bound of that particular interval is increasing as well. Okay, so if you increase confidence interval, then what happened? Okay, so we can say if confidence interval is increasing, then the width between these lower bound and upper bound is also increasing. Okay, so there is a problem, right? What is the problem? We cannot increase our confidence interval as we want. Okay, there should be some like cutoff marks. Okay, but again, that depends, that particular confidence interval depends on your problem or general problem what we have in the outside. Okay, it depends on that. But under this course, I mean, if I ask questions, I'll give you the confidence interval, or sometimes you can find the confidence interval, so no problem. But in general, once you are dealing with the real data set, not in this course, but if you are dealing with that, you have to find the best option for the confidence interval. Okay, 95, 90, but these three, 90, 95, 99, those are the confidence interval we are used like almost all, not all three together, either one. Okay, clear? Okay, lower the confidence level, the results in lower critical value, right? Increase, okay. How do we reduce width? So we need to reduce width. Okay, so we can pick lower confidence level, like if I consider 99 and 95, I can pick this guy instead of 99, something like that. But again, it depends on the problem. Okay, keep that in your mind. Once we increase the sample size, if I increase this guy right over here, increase, you can see that this portion or this piece become smaller, right? Plus or minus become smaller value. So x bar plus or minus a smaller value, it remain very close to x bar. Clear? So once we increase the sample size n, we can reduce the variability, or we can remain around the mean, sample mean. Okay. Okay. Check this example. Same example I used a few slides ago. Few minutes ago. 100 cans and 400 cans. 100 can case we have done. Okay, few slides. 4 or 5 slides before we did that. Now consider 400 samples. Same values but different n. See, now it is 400, and you can see those two boundary values. I think I have mentioned here the next, this one. See, this is the previous one. Blue color values belongs to 100 samples. So you can see this interval. You can compare this red color and blue color intervals. See, red color interval, okay, that interval, the width of that interval is less than the blue color interval length or interval width. Clear? So when we increase the number of samples, it is possible that we have smaller interval. Yes. Bigger or not, the width. See this one 0.7. See, sorry, 12.0704 is somewhere here. Okay, but 12.7 0.051 here. Okay, I mean if you check those values in the real axis, it's like this, right? So this is my real axis. So what's the next value? This one, 12.1096. What is this value? 12.129. Okay, so below the real line, you can see these two values, blue color values. Okay, once you check the gap, yes, once you check the gap between these two values and these two values, you can see smaller values goes to here, smaller width. So that's how we get the smaller one. Yes. It doesn't matter. Doesn't matter if they have mentioned keep the like keep the 4 digits, or I mean keep the 4 decimals, you can keep it. But here you can check, see, it depends on the values. Here you can get 4 decimals because of this value. Here it based on this calculation. Okay, so if they ask 4 decimals, 4 decimals. Otherwise, if they I think they haven't I mean they haven't mentioned anything about how many decimals you need to keep like 2, 3, 3, that's fine. Okay, there is no problem with that. Okay, okay, so minimum n. Okay, you saw that once we increase the n mean number of sample size, we can get much more better confidence interval. Okay, there is a way to find the minimum sample size that we need to use using this equation here. Using this equation here, you can find the minimum sample size that we need to get a better confidence interval according to our C alpha over 2. Okay, which means according to our confidence interval, Ci. Okay, so here critical value C alpha over 2 is critical value. This is a C-score value, but once we are using it with alpha, we call it critical value. Okay, this is a C-score value. C-score value. But once we are dealing with alpha, those stuff, so we call it critical value. Okay, different name but same idea. W is the width, desired width within this interval. Okay, sigma is the population standard deviation. And remember that if you need to find the n minimum sample size, always round it up. Okay, always round it up, like 12.3, round it up. It doesn't matter whether it is less than or greater than 5, round it up, which means this is 30. Why is that? I can show you here. You have once you calculate it, let's say you have this value 58.2, so you can consider 58 or 59, right? Once you use 58, it is little bit wider. I mean the gap between lower bound and upper bound for this 58 observations is much bigger than 59 observations. Okay, because of what? Sigma over square root of n. This portion here for sigma over 58 is less than sigma over 59. Clear? That's the reason. Okay, that's the reason. So always try to round it up. It doesn't matter what's the decimal, 0.1001, doesn't matter, round it up. Okay, this is a level of, okay. Check this example. I think this is the last example that we have. sorry, this one. Wish to construct 90% confidence interval within 0.5. Okay, check this word within. Logs assume population standard deviation given. So what is the equation? 2 times C alpha sigma. So n equals 2 times C alpha over 2. 2 times C alpha over 2 sigma over W, right? If I'm correct. Yes, sigma over W. Square root, sorry, not the square root, squared. Yes, squared. This is your n, right? This is how we find it. What is this W? Width, gap between lower value and upper value. See, they have given interval within 0.5. What's that mean? Is that equal to width? Width equals, see, within, don't forget this one, within mean half of the width. So you have to multiply by 2. Width equals, if they have given within that keyword, you have to multiply it by 2 and plug here W. This is W. Okay, so don't forget it. Within mean half of the width, which means plus or minus 0.5. That's the idea behind it. Within mean plus or minus 0.5. Okay, so I'll erase this. So once you plug those values, you can get, see, 249.38. Round it up 250. Do you have any questions from 7.1? Okay, because these chapters 4, 6, not 6 is not big deal. 4, 7, those are very good sections or very good chapters to give you questions. There can be more questions from these two chapters. Distributions from, I mean, chapter 4, this one, because these things we are using a lot. That's why we can give more questions, because interval, confidence interval, point, sometimes yes, point estimators, we use a lot. Okay. Okay. Let's go to, oh my God. Let's go to the next one, 7.2. In this case, we are talking about what happens if we have a large sample, which means n is much bigger, like 100, 200, 1,000. Okay, just now we stop from there, right? Large sample confidence interval. What happens? Does it change or remain same? Still confidence interval. Do you remember the population previous case? We used few assumptions for the point estimators or confidence intervals. Yes, SRS, which means we pick our data using simple random sample. Okay, that method. So there is no error, sampling error. We assume that. Exactly. Okay, variable is exactly normally distributed, which means population is normally distributed. Okay, that's we assume that. We do know we know the population standard deviation sigma. Population standard deviation sigma. Okay, these three we assume. Okay, it remain. We know these things. Okay, which means it satisfies these three. Okay, what happens if one of these get failed? Okay, if it violate one of these, still we can use our techniques, but with different, I mean, with few adjustments. Okay, with some adjustments. What is this space? Okay. Okay, if we have simple random sample, n is large, but they haven't mentioned that our population is normal distributed. Okay, Thing is, if n is large, I would say if n is large enough, that's the word. N is large enough, we can approximate our sample is normally distributed. That's why they have mentioned this x bar is approximately normal distributed. Which means our sample is approximately normal distributed. We can assume that. So don't ask me what is the value for n, large enough value. There is no cutoff mark. It can be sometime like very basic level we use 30, but it's not the cutoff mark. This course I think we can use 40. Okay, but don't stick with to that. Stick with to that value. It's not the recommended value. Okay. Okay. It follows that the same confidence interval equation doesn't matter. It doesn't change. So confidence interval level of this confidence level. Okay. Now it's not 95, 100 times 1 minus alpha percent. Okay. General case. Okay. Yes. What happened if we don't know what is population standard deviation? Same as what we did in the first few chapters, we can replace sigma, which means population standard deviation, using sample standard deviation. Okay, but if you remember, once we get that value, that z, capital Z value, it becomes like this, not x minus mu over sigma, right? Clear? If we know, okay, if we know sigma, then you can write C equals like x bar minus mu over sigma over square root of n. Clear? But here we don't know sigma, so we replace sigma by s. Okay. Okay, has an approximately normal distribution for large n. Okay, for large n, you don't need to worry about that. You can simply assume that it is approximately normal distributed. For large sample confidence interval, okay, replace like this. This equation in the previous case, this equation, you don't know sigma, so you can replace sigma by s. So same time, you can calculate the margin error of the margin, z alpha over 2 times s over square root of n. Okay, using this margin of error. How much error do we have? You can calculate using this. Okay, clear? Don't think too much. Just get the idea and practice with these equations. Okay, because equations are given, you don't need to worry about that. Okay, when is this confidence interval valid? Okay, here the thing I have mentioned. Okay, simple random sample here, unknown mu and unknown sigma. Yes, Ci is still valid. The population distribution can have any shape. If n is not large enough, it can be anything. So you cannot deal with the confidence interval. If you don't know these two, at the same time, you cannot use confidence interval, except you can assume it is normal distributed, or you can get the S, standard sample standard deviation. Okay, population can have, yes, any shape, but if it's large enough, which means for this course we consider greater than or equal, that's fine, greater than or equal 40. Okay, it is not a good cutoff mark, but right now we can use it. Okay, you haven't done this part. This is section 5 stuff, central limit theorem. If I have enough time, I'll do that. Strict that. So okay, smaller sample, we must significantly different approach. We will talk about for small sample in section 7.3 because it is totally different. Totally mean it's different. Okay. Okay. I have just 5 minutes. I'll do this example and finish it. Okay. 95% confidence interval. Sample is 50. See 50. What is this? Sample mean given, X bar given this much. Sample standard deviation given this much, which means S. Okay. Okay. So you can plug these values into your equations. So into your equation X bar plus or minus d alpha over 2 S over square root of n and find the confidence interval. Okay. Based on 95. Here they have mentioned two-sided. Two-sided mean this. As I mentioned before, two-sided mean this. Alpha over 2, alpha over 2. This is we call two-sided. Okay. There are, yes, we have to discuss one-sided as well. I think few slides later you will see that. Okay. If it is just confidence interval, definitely it is a two-sided. So you have to get the alpha over 2. No problem with that. Okay. I'll talk later what is the one-sided mean. Okay. So plug these values into this equation and get the corresponding confidence interval. Okay. Okay. I didn't tell you why we can use that. I mean, why we can use this equation. I didn't tell you. Please don't forget those conditions. Here, they haven't mentioned anything about the population. We don't know whether population is normal distributed or not. But we assume that our sample is approximately normal distributed because this. We have large enough sample size. Okay, clear? See, it's greater than 40. We can assume that still we don't know about the population, so don't talk about the population. Population is not normal distributed. We don't know that. But sample, we can assume that it is normal distributed. Clear? So then you can simply use this equation. Okay, clear? Okay, this I'm going to stop this point.